Hi, my name is Guy, and I'm presenting a joint work with my advisor, Yoram on using null messages in a Byzantine setting. Dealing with faulty processes is a major part of distributed computing. In the Byzantine failure model, processes can deviate arbitrarily from the protocol. The mere possibility of these failures, even in runs when they do not occur, significantly complicates the use of messages in this model. A key aspect of Byzantine failures is that a process cannot trust the content of a message it receives. For example, here, when K tells J that I want to meet him, it might be true, but J should also consider it possible that I told K the exact opposite and K is simply lying. A typical way of coping with this is by sending many messages to convey a single piece of information. If many processes tell J here that I said that it wants to meet him, then at least one of them is correct, and now J knows that this fact is true. This causes many protocols in the Byzantine model to require more communication than those in the crash failure model. For example, polynomial T+1 round protocols for consensus in the Byzantine model require much more communication than those in the crash failure model. In many settings, failures are infrequent. In such contexts, we may wish to optimize for failure-free executions. For example, if you're always driving as slow as if there are potholes in the road, then your typical 10-minute drive to work will always take an hour. In this work, we do exactly that, failure-free optimization for Byzantine consensus. That is, we want to design protocols that are very efficient when no failures occur, drive fast when there are no potholes, but are resilient to failures if they do occur, slow down if there is a pothole. We consider the standard consensus problem by Pease, Shostak, and Lamport, and processes less than third are Byzantine faulty in the synchronous setting. Every execution must satisfy agreement, validity, and decision, and we want our solutions to be efficient in both time and communication. To this end, we note that null messages, that is, communicating by not sending a message, is especially valuable. In TCP, for example, the cost of sending a single bit message is similar to the cost of sending a 1000-bit message, and it is much more than the cost of not sending a message. This is because sending a message requires memory resources, network resources, energy, etc. In many network protocols, sending only a few bits of information in a message is just like using a huge heavy package to send a simple greeting card. In our work, we present a modular way to transform any Byzantine consensus protocol to one that is efficient in failure-free executions. We do this by designing very low-cost layers consisting of only 3 or 4 rounds that will solve consensus if no failures occur. When failures do occur, control is transferred to a Byzantine consensus protocol of choice. The result is a solution that is extremely efficient if no failures occur. And in case of failures, add only a low overhead to the cost of Byzantine consensus protocol used. I want to emphasize that the choice of this Byzantine protocol is up to the designer. The solution is modular and will fit any protocol the designer chooses. This allows customizing the costs of the solution according to the designer's preferences. The reason our solutions are so efficient is because our layers make extensive use of null messages, and in particular, a primitive we call silent validation round. I won't define silent validation round, but let me illustrate what we mean by an example from one of our layers. In this example, there is a committee that recommends decision values to all the processes. Here they send the recommendations. A process that receives a unanimous recommendation remains silent in the following round. In particular, if every process received a unanimous recommendation, no messages are sent, and the round is completely silent. At the end of this round, a process that received no messages is guaranteed that every correct process has received a unanimous recommendation. Hence, it can now decide. For more details, see the paper. Silent validation rounds allow us to broadcast global information with a cost of a single round and no messages whatsoever in failure-free executions. This is a very useful primitive that we apply in several ways in our layers. In the paper, we present a number of layers with different properties, and the resulting design is efficient and elegant. To summarize, we provide modular solution to the classic Byzantine consensus problem. Our solutions are lean layers that are prepended to any chosen Byzantine consensus protocol. The resulting solution has the best known failure-free behavior, and in case failures do occur, has in essence the same behavior as the appended consensus protocol. We make considerable use of null messages and define the useful primitive of a silent validation round. In a broader sense, in asynchronous systems, information flows only via message chains. In synchronous systems, however, timing allows information to flow in many possible patterns. We have demonstrated how this could be effectively used in the more challenging Byzantine model. This is another example of how time and silence can play a key role in distributed computing. Thank you very much for listening.